Okay, so my name is Manya Raman Sundström. Actually, I just go by Manya Raman when I publish, and you can call me just Manya. It's fine. I'm originally from the States. I work in northern Sweden. My background is a little bit in math, but mostly math education. And I really like to know who I'm talking to, so I just want to ask you a couple questions. How many of you, I just want to know who you are. So raise your hands to these questions. You can raise your hand as many times as this feels appropriate. What do you identify yourself as? A mathematician? A philosopher? A historian? Math education? Someone in math education? British spy? Anything else I missed? Anyone else?
Piano playing?
Psychologist.
Yeah, musician? How many musicians?
Isn't it great?
Sorry? Psychologist?
Psychologists. Yeah.
Alright. Okay, so another question that's directly relevant to my talk. The goal of my talk is to try to connect beauty and explanation, two of the strands that we talked about so far in this conference. I'm just wondering how many of you have thought about that before? Whether beauty and explanation are related? Okay, and how many people think they are?
We are beautiful or what?
That beauty and explanation are related. Yeah. I'm just going to say, for the people who have not thought about this before, I'm just going to say a little bit about why this might be an interesting question. There are many reasons you can give. I think it's not obvious that they might be related, and actually pretty hard to prove this. So what I'm going to talk about is sort of ongoing work. I hope to get through a bunch of examples and have some time for discussion because it's really ongoing for me and I'd love to hear what you think. A couple of reasons why this is an interesting question. One is in philosophy of mathematics, we don't have that much to go on about what beauty is. We have a little bit to go on about what explanation is. So if we can connect these two, then perhaps some of the models that we have for explanation might be brought to bear on what beauty is. It may not work, the project may not work, so it may not be true, but if we do, we have some theoretical tools. Another thing, we're talking a lot about values in this conference, and within math education, in any case, explanation is something that's often talked about as valued. We talk about the distinction between proofs that explain and proofs that demonstrate, and usually proofs that explain are those valued a bit more for some reason. They're somehow privileged above those that merely demonstrate. The case for beauty has not been entirely made, I think, especially when you look at curriculum documents, what we teach, what we value in terms of our education. So if we can find a connection between beauty and explanation, there might be a stronger case to make for some of the aesthetic values we might want to have in teaching. But let me get to the talk. So this is what my talk's going to look like. The central question, are beauty and explanation related in mathematics? I'm not going to talk about explanation in science. I'm not going to talk about beauty in the arts, just restricted to mathematics. And my suggested answer, we'll see if you buy it or not, is that they might be related to the concept of fit. So I'm going to talk about what fit is, and I'm going to talk about two different kinds of fit, intrinsic fit and extrinsic fit, and try to give you some characterizations of what these things actually are. And then Matthew's going to do a survey and get people to say that they're not related at all. Okay, and this is what my talk will look like. These are the different stages. I'm going to first give you a little bit of context about some terms and where my study is located. I'm going to talk about the motivation. Why is it that I believe beauty and explanation might be related at all? See if you buy my example. I'm going to talk about some limitations. So even if beauty and explanation are related, the relation is neither necessary nor sufficient. So I can give you an example of a beautiful proof that's not explanatory and an explanatory proof that's not beautiful. They're not connected that closely. So I'll give you some examples of that. But I'm going to hopefully be able to convince you that the two might be related anyway through this notion of fit. And the last part of the talk, which will be highly speculative, we'll talk about what fit might mean in mathematics and how it relates. Okay, so the context. Most of the research I've done has been carried out in the context of a seminar on mathematical beauty held at my university This is sort of an interdisciplinary seminar, mostly mathematicians attend, but also sometimes philosophers, people interested in linguistics and computer science and so forth. And what we do every week is we either read a paper on beauty and their explanation or related topics, and the other weeks we present proofs. So these are some of the proofs that we've presented that people just say, okay, this is something I think is beautiful, and often they talk about a theorem and they actually do several proofs, so we compare the different proofs and say which ones are beautiful and for what reasons. And I'm going to take from this set of examples a few to talk about in a little bit more detail. Most of these are sort of simple ones. Problem with most of these, actually problem about giving a talk about beauty in mathematics or beauty in mathematical proofs at all is that most of the examples, if you really want to get into something meaty, would take more than an hour to present. So most of the examples I'm going to give in this talk are fairly simple. You've probably seen them before. You've probably thought about them before. But I'm mostly interested in the connection between beauty and explanation. So hopefully having examples that are fairly simple will be an advantage, that we can focus on that. There's also extra examples. I've asked a bunch of questions on Math Overflow, so if you want to see, there's a ton. I think I got now over 1,000 hits on my question about what are examples of beautiful proofs accessible at the high school level on Math Overflow. So I think there are 42 answers or something, if you want to see some more examples. Okay, so I'm going to just tell you the term. So another problem about talking about the relationship between beauty and explanation is we don't really have a good definition of beauty. We don't have a good definition of explanation. So for the most part in this talk, I'm just going to ask you to use your intuitive ideas of what those things are. But I'm going to nail it down a little bit more. So for beauty, these are the assumptions I'm going to make. I'm going to assume that beauty exists in mathematics. Not everybody thinks it exists, but I'm going to take that for granted. The question about whether it's objective or subjective, I'm going to leave that question open for now. This is a little bit problematic for me because I'm doing sort of a combination of conceptual analysis and I'll also use empirical data. So I have mathematicians tell me whether they think proofs are beautiful or not. So whether beauty is an objective concept is sort of relevant to the kind of work I do, the data that I have. And there are times when the mathematicians say, this proof is not beautiful. And in our analysis, we think it is beautiful. And what do you do when you have a mismatch like that? So the questions of objectivity and subjectivity definitely come in, but I'm not going to take a stance on that right now. We're going to consider, similar to Matthew Illinois, beauty, elegance, cleverness, all of those things as one sort of set. I don't really care right now. Right now it's just sort of something positive. I like this proof. I like this proof better than I like that proof. And actually I'll get into trouble for having done that at some point, and where I think you really do need to tease apart what those words mean specifically. But for the most part, for most of the examples I give, it doesn't matter. Beauty, it's beautiful, elegant, cool, whatever. It's nice. And for this talk, actually for my study, we're just focusing on mathematical proofs. So there's many things in mathematics that can be beautiful, theorems, definitions, diagrams, etc., but we're just going to focus on proofs. Okay, about explanation I can say a little bit more. There are, as Matthew actually gave examples of some frameworks for explanation in mathematics. There's still a lot of debate about what it should be. But the one thing I want to highlight is there's a lot of things explanation can mean. So this is a list of some of them from Hafner and Mankosu. Look at that. For the purpose of my talk, all that matters is that explanation gives you a sense of why a claim is true. But all of these have a little bit different nuances, and it would be sort of incorrect to just plow through the talk without at least recognizing that explanation could mean many, many different things that are worth teasing out. And there are these different models. I'm not going to go into them very deeply. From the 70s, Mark Steiner's model characterizing property. He, by the way, suggested this in contrast to things like generalization as being something involved in explanation. So the more general proof doesn't always explain more. Kitcher talks about unification or explanatory store. That was in contrast to covering laws or rules. So there are these ideas that you have these laws and then everything falls under one of them. No, and then it says picture, there's some sort of unifying idea. And that the idea of unification will come up a little bit later, so I'll highlight that. And there's work being done even now. Mark Lang has a paper, hasn't been published yet, but he's circulating it. And he talks about a couple of key, what he thinks are the key components of explanation: saliency, unity, and symmetry. Symmetry is kind of a funky thing. I don't know if you guys think that. How many people think symmetry is involved in beauty?
Involved.
Did
you find that's involved?
Sometimes, often.
In beauty, it's more complicated.
Yeah. But I think it's kind of funky that these terms are not in the context of explanation, they're in the context of, they're not in the context of beauty, they're presented in the context of explanation. And this is actually, this paper that he wrote was one of the things that started getting me thinking about whether beauty and explanation were related, because some of the ideas that he had and the examples that he has in his paper that he called explanatory also seem to be beautiful, and the reasons that they were explanatory seem to possibly be reasons which certain proofs could be beautiful. So I'll get into some of these characteristics a little bit more in detail later. Okay, so first example, same example that Paul used actually. It's a sort of standard place to start. And I like that he used this example as an illustration of a canonical thing that's beautiful, and I'm going to use it as a canonical thing that's explanatory. So that gives you a little bit of the instinct or the intuition behind why, beauty and explanation might come together. So this is the arithmetic sums. You're all probably familiar with this. And this example is actually used in Steiner's paper from, when was it, 1978? Anyway, this is a classic example that's used to talk about explanation. So Steiner first gives a proof by induction, and this is supposed to be an example that is really not explanatory. Are you familiar with this one? So you just see what happens in the k+1 case, break it down, do the algebra, and you get the formula. So I take this as an example of a proof that is not explanatory, not beautiful. And then the classic proof that's given in contrast to that as an explanatory proof is the one you probably saw in 5th grade, where you sum up numbers 1 to n, then you reverse the order, call it s prime, which is the same as s. And of course, when you do all of the column additions, you get n terms, which are all n plus 1. So the sum to s is equal to that. So s is equal to n times n plus 1 over 2. So this one is suggested as an explanatory proof, and Steiner uses the word illuminating. So I can just stop and see, in this room, do you think this is beautiful? Raise your hand.
Not the way you did it.
Okay, well, I'll ask you a less loaded question. How many think this is nicer than the induction proof? Okay. Yes, John?
I think what I would call beautiful is the idea,
Yeah.
not the proof itself.
Good.
Yeah, but then here, induction.
Thanks. I think so too.
Yeah, that's a wonderful one.
Okay, so and of course this is another way to represent exactly that thing. So even if you didn't like the format of the one that I presented before, this is another way to represent it, classic representation. So this is one of the sums on the bottom, you reverse it and put it on top. So that gives you the n times n plus 1 over 2. What do you think of that one? You like that better?
No. Not at all.
No? Okay. Because?
Let's
Well, it brings in a picture that doesn't help me, and gets rid of the nice column structure, which I think is quite pretty. It's a neat idea, the column structure. That seems to be like dressing it up.
That's interesting. So the idea seems less accessible in that case to you?
That's proof, but
That's less beautiful to you than that one?
yeah.
How many people share that intuition? The front row. let's see. One thing I'll just mention about this particular proof is actually not as general as the previous one. It's a specific case. So all the work you do to if you make it work is done in your head. So it's just a presentation of one case where you can, if you have the right level of understanding, you can get the main idea and sort of generate it yourself. Yeah, so this is an open question if you consider this more beautiful. I actually thought more of you would think that this is more beautiful. In our seminar, this was considered the most beautiful. This was considered more beautiful than the...
But it's not a proof.
Yeah? Yeah?
Is that the same as the teachers?
I haven't done this yet with teachers. That's what we should do that, but
No, but
So who's in your seminar?
mathematicians. Yeah.
That's weird because there's no N in it. I really don't like the fact that
Okay. If I give you the same picture and I put n and n plus 1, would that change
You
your...
can't.
No, but we just had this discussion here in the back row, and they said the end is in my head.
Yeah.
I see the end
How's that
here,
picture have
although
dots
it's
in
not
it?
Yeah, but that's
Yeah, but I don't like the 5 and 6
interesting.
kind of
Macro
distortion.
has a fight against the formula.
It's
Yeah.
not a proof.
It's not a proof, okay?
Is it not?
Not
Yeah,
really.
John? John?
What might be beautiful or certainly interesting is that it might be a vehicle to provoke generalization rather than requiring me to interpret someone's generalization in the previous slide.
Mm-hmm.
So it's actually provoking an action in the viewer,
Yeah.
which seems to me to be, at least pedagogically, a useful
the
move.
interesting thing about it.
Yeah.
In defensive pictures, you could have, you could have like 7 cases, right? 7 squares,
Yeah.
and then put dot, dot, dot,
Okay.
and that would capture the general.
Not for Jeremy, but okay.
Some
Well,
sort
we can leave this as an open question. Maybe they're different subjective judgments. I'm not going to push one on you. Okay. But anyway, this is what got me thinking about whether there's a link between explanation and beauty. At least in our seminar, we have had a number of proofs where we had a more explanatory proof and a less explanatory proof. And it seemed almost all the time when we had a more explanatory proof, people considered it nicer and possibly more beautiful than the one that was not explanatory. So we started to think, is there some reason to believe that explanation has anything to do with beauty? So we looked at a bunch of examples, and I can tell you, like I said, I can give you examples of beautiful proofs that are not explanatory and vice versa. So I'm just going to show you some. Okay, not all beautiful proofs are explanatory. How many of you seen this proof? I'm afraid you can't see the little notations, but
What's the proof of?
it's a proof. Actually, it's a derivation. I shouldn't really say it's a proof, but it's a derivation of the formula from a point to the line. And this comes from a paper from Tommy Dreyfus and they gave this out to a bunch of mathematicians also and asked them to describe, to compare how they think of this derivation versus classic derivation. It's classic derivation, you can parameterize things and sort of just, compute the formula. But this is kind of cool. So I take a point here connected to the line. So the point on the line has coordinates A and MA plus B. And I have a triangle. This triangle here is right. Now I'm going to make another triangle inside, and this is the distance I want, right here. And then I have this other triangle inside. This unit is 1. I'm just constructing it to be 1. And this height here is the slope. Because, it should be, right? Do you see the cool thing? They're similar triangles. You see that? Because these two lines are parallel, so you get the same angles. And because they're similar triangles, you get the nice proportions of the lengths of the sides. So PQ, this is the long distance here. And that's equal to, just if I subtract the y coordinates, MA plus B minus C. That's what that says. So if I look at the distance of this leg D over 1, that's going to be the same as the hypotenuse, which is the MA plus B minus C over the hypotenuse of that little triangle, which is square root of 1 plus m squared. And that gives you a formula. That's it. You think it's beautiful?
Not from the first sight.
So this, I'll leave you to think about your own judgment about it, but in the study that this came from, it was considered, actually the word just to be fair, the word that they used was elegant. They didn't use the word beautiful, so I don't know if that may be an instance where you don't want to group elegant and beautiful, but it doesn't seem to be explanatory. I don't think you can see from that proof why anything about the meaning of the formula or where it comes from, it just falls out because of the relationship. Is that true? You think it's explanatory?
Tells you where the denominator is coming from, doesn't it? I mean, if you just saw that root 1 plus m squared, where's that come from? Now you see where it comes from.
And there's a kind of contrast in mind, isn't there, with the kind of brute parameterized calculation,
Yeah.
right? So when you say, oh, this is elegant or neat or tidy or something, you have that contrast in mind. And most things are going to be tidier than that.
All right, so we can do a straw poll. How many think this is explanatory?
Yeah, I think you need to measure how far our hands go up, actually.
What's that?
To some extent.
Yeah, there should be
Wow,
there should be some buttons here so you get to push, like, so we're confident about that, or a little bit, or yeah, there may be scales actually. So these are some things that we're gonna. I should just say all we've done so far is pilot work. So we want to test these more broadly. So we want to sort of, do some broader empirical studies. I don't know how reliable our group is. Yeah, we didn't think it was explanatory. And by explanatory, I mean why it's true. So do you see why? So seeing where something comes from, I don't think is the same thing as saying why it is the way it is.
You have some background, maybe the views from where it comes from. It's very personal, I think, how your mind is oriented, where you see your background, the concepts you have, how you can connect them. It's kind of very particular.
Yeah? Yeah. Okay, well, maybe it's not a limitation, maybe. That would be great, I'll be happy if it's not a limitation. Okay, there's more examples of this, so I asked on Math Overflow if people could give examples of explanatory proofs or beautiful proofs that were not explanatory. So if you want to see the results so far, Terry Tao has answered. He's suggested the four-color theorem and there's a little bit, on the Math Overflow, there's a little bit of discussion, so people have at least given some reasons why and debated them a bit. So there's a little bit more sophisticated examples. I'm not sure the one I have is the best example, but it's one that I can say in 5 minutes or less.
So,
I don't even know. Yes?
What is being said about what proof of the four-color theorem, sorry?
Terry Tao claimed that the proof, I think the standard proof is beautiful, but it's not explanatory.
He's a very smart mathematician, but is that the one where you proceed by just eliminating millions of cases on computer, really? Well, that strikes me as most uniquely repellent.
He has a justification. Yeah, I don't remember what his name, but you can go look on Math Overflow if you want. He has a justification. He has a justification for why he thinks that's beautiful.
But I think maybe the proof of the four-color theorem is the monstrous thing where you discharge 1,500 cases on the computer. Proof of the five-color theorem you can do on a whiteboard, and it does have a sort of feeling of elegance about it.
Yeah. Yeah.
And I don't know which one he's actually talking about.
Yeah. And it's the complicating factor. I don't even know if these judgments are objective, so, maybe Terry Tao BB is not the same as Jeremy Gregory BB. So I don't know.
I defer to him, but wow.
Wow, okay. Another limitation, so I think not all explanatory proofs are beautiful. This one was from my dissertation. So sorry about it, but this is one I know well. Prove the derivative of an even function is odd. So on the left is what a lot of mathematicians did when I gave them this. Prove the derivative of even functions. Okay, look at a canonical even function. The slope at x is the opposite of the slope of minus x. I can see why that's true. Then they had to write down some stuff, but that was sort of the key idea. That gave them the idea why the claim is true. So that's explanatory. Another approach, and this is sometimes what they wrote down even if they had that kind of insight, is to just use the definition of derivative. So f prime of minus x, write out what that is, do some algebra, do the right substitution, and you get minus f prime of x. You're done. So this is a case of a proof that demonstrates. It's just showing that it's true. And in this case, okay, so in this case, I have an explanatory proof and a non-explanatory proof. I don't think the explanatory proof is all that beautiful. It's explanatory, but does anyone think it's really beautiful? Yeah, could be. You think it's beautiful? Okay, great. Then it's not a limitation. I'm not sure. This one makes me nervous because I don't think it's so interesting. But maybe it depends on your orientation to it. There's been a question in related to beauty of mathematics if your familiarity with something makes it less beautiful. So the fact that this was in my dissertation, maybe I cannot see the beauty in it anymore. But if you see it for the first time, maybe you can kind of see that better then. So, okay. Okay, so these were my worry cases. The first one's a proof that's explanatory, a beautiful proof that's not explanatory, an explanatory proof that's not beautiful. They may or may not be, maybe I'm wrong, maybe I don't have to worry about them. But the general thing I want to get at, and the point I want to make, is that maybe even if there are worry cases, and there are better worry examples than even the ones I've shown, that beauty and explanation are related anyway. And that's what I want to get at. That's what's interesting. What can they be related? And I'm going to try to argue, or at least put forth the idea that they might be related through the notion of fit. The metaphor of beauty is fit. So I'm going to tell you a little bit about the metaphor of beauty as fit, and then try to connect them to mathematical examples. I have no idea how I'm doing on time, by the way.
Not that great.
Okay. Then no more audience interaction. Okay. So metaphor of beauty is fit. So this metaphor has been around since ancient times. Metaphor of beauty is fit. It's been used in art. It's been used in lots of other contexts. And mathematicians talk about it too. So this is a quote by Hardy, which maybe you've seen before. Ideas, like the colors of words, must fit together in a harmonious way. Beardsley also talked about beauty as fit. He's a philosopher, if you don't know that. In his talking about the aesthetic experience, he says, beauty is a feeling of things working or have worked themselves out fittingly.
That's a different meaning of fit.
Yeah, there are many different meanings of fitting. Natalie Sinclair, she uses the word fit in this quote about 5 times, and each one is a different sense of fit. She talks about fit in the process of doing mathematics, and she was exploring something called Napoleon's theorem in this example. Both the visceral feeling generated by joining the vertex to the edge and the exactness of the integer after my first construction gave me a strong visual sense of fit. Making that connection to Napoleon's theorem invited me to recognize area geometry. It was also gratifying to realize that a configuration I had looked at and played with many times before held more treasures, etc., etc. She talks about chess fit in many different ways in terms of the connection of this theorem to a whole class of theorems, in terms of her own thinking about why it's true. Okay, but what exactly is fit? And what does it mean? And what does it mean in the context of mathematics? So I'm going to talk about a distinction between 2 different kinds of fit, one called intrinsic fit and one extrinsic fit. Intrinsic fit refers to the relationship between a proof and the underlying ideas. Extrinsic fit deals with the relationship between a proof and a whole class of proofs. So the first one is sort of an internal thing. How well does a proof fit its underlying idea? The second one is more global. How does this fit into a family? So it's a family relationship. I'll give you an example. So I'm going to start off with 2 different proofs of the Pythagorean theorem. The first one I claim has an intrinsic fit, the second one doesn't. So you've probably seen this before, it's from Euclid, it's the not so famous one from Euclid. So you take the triangle, you drop an altitude, and these two triangles sum up to the whole one. They're similar, so you can sort of fold them out, you can see that this one plus that one is going to equal that one. And the fact that their triangles doesn't really matter, all that matters is that the areas have this relationship, so they could be squares.